And next speaker is Bob Miller, who I think has possibly come furthest for this conference, and if we thought carefully we want to put you on tomorrow. Jet lag. Bob is from the College of Earth, Oceanic and Atmospheric Sciences at Oregon State, and he's going to talk to us about the use of the implicit particle filter in high-dimensional systems. Thanks, Bob.
Well, thank you, Andrew, and thank you for asking me. I'm delighted to be here. I've never been to Cambridge before, and I'm actually happy to be on today, jet laggy as I am, because I'm a stressy kind of person, and on days when I'm giving a talk, I generally don't hear anything. The world goes right by me, and so it's just as well that I'm be done early. I'd be able to pay more attention, even though the talks so far have been so good that I've been able, actually, jet lag and all, to find them interesting. I hope I can keep up. Today, I'm going to talk about some work that I've done with, hello? Goodness gracious. There we go. Where are you? Some things that I've done with my colleague Yvette Spitz and Brad Weir, who was a postdoc with us. He's now departed, works at NASA Goddard. We had originally looked to do biological models. I will not be talking about that today, but I'd like to talk about the sort of stuff that we've been doing over the last few years. The implicit particle filter is one of several recently proposed particle filters. I guess in this audience, I should go over exactly what the general framework here is. What we in the Oceans and Atmospheres community call data assimilation is what a lot of is a term that comes from numerical weather prediction. If you were going to predict the weather, you got this big system that presumably solves the equations of motion for the whole atmosphere. You need initial conditions, which of course you don't have. Because what if it rains in the middle of the Pacific Ocean someplace and you don't know about it? There aren't ships out there to see it. The satellites can see it, but have limited ability to resolve exactly what's going on down there. So you take your best guess at initial conditions, you solve the equation until tomorrow. Tomorrow comes, and you find out inevitably that you were wrong. And so now you need new initial conditions to go on. And so one thing you could do, I guess, is you could just throw out your model and take all the data that you have and start over, but you don't want to do that because you had some skill. And the data are still sparse, and still you got the same problem of what happens if it rains in the middle of the Pacific Ocean. You don't know. And so over the years that people have been trying to predict the weather, since weather prediction has been an ongoing exercise, the model is said to assimilate data. And we tend to have gone back to the same well that I was happy to see our colleagues in molecular dynamics go to, which is basically the machinery of Gauss-Markov least squares, sorts of Gaussian stuff. We tend to follow the engineering approaches, the folks who want to do something like navigate that airplane that brought me here. You know where you are. You know you have data from, you know how much fuel is going into your engines. You know, and you have a course in speed from a second ago. A second later, you guess where you were because you knew your course in speed. But now you have a new radar fix. You have GPS. You have everything else, and you want to update that. And we tend to have, and the Oceans and Atmospheres community, the Atmospheres community before the Oceans community certainly tends to use techniques that come from that sort of approach. Come on, wake up. I don't. Can I unset the energy saver? Thank you, Eric.
Or just plug it.
Oh, maybe is there a plug? Because I should have brought my plug. Because I have an American plug, but I did have a plug in it. There, let's hope. Well, I start with the notion of particle filters. The idea generally is that what is actually done in the weather centers and what is the sort of natural thing to do is least squares. You make assumptions about error covariances, and then you combine data with models in exactly the way we saw done this morning in pretty much all of the talks. But if you make these Gaussian, but if you look back at the engineering literature and you look how that sort of thing is done, it all comes from assumptions of linearity and normality. You assume that the dynamics are roughly linear. You assume that all the random processes are Gaussian, and then basically all that you need to know about a Gaussian distribution is the mean and the covariance. And so you look at tracking the mean and the covariance. But the ocean and the atmosphere are very highly nonlinear systems, and it does happen that these assumptions are violated so badly that you have to go on to do more general, to treat these phenomena more generally in order to avoid being led astray. That is, sometimes these systems are so strongly nonlinear, and sometimes the statistics are so far from Gaussian that you can be led astray by these simple methods. And the other thing is that these nicely rigorous methods that go back to Gauss himself are based, sometimes can fail entirely. You can try to compute them and nothing happen. And so we resort, the real solution to a data assimilation problem is not a mean and a covariance, but a probability density, but a conditional probability density. We look at the ocean and atmosphere as having a state vector, usually a fairly simply defined state vector that is velocity components and a density, or in the ocean, velocity components and a temperature and a salinity at every point on a grid. And that is our state vector. And if you look at that as a stochastic quantity, you're interested in its probability density function. And if you have actual observations, if you assume that what you're looking at is a stochastic process, then you make an assumption that sounds a little strange in the world of atmospheric science, but I would guess this audience will be quite comfortable with it. This is a stochastic process, and on any given day the atmosphere is exhibiting one realization. And ideally we assume that we know the dynamics, we just don't know which realization we have. and so in fact, the name of the game here is to try to estimate a probability density function, the probability density function of the state of the atmosphere or ocean conditioned upon observations. And in general, you can't do that for the ocean or atmosphere, because even a small model, the ocean or atmosphere, has a state vector of enormous dimension. And so these probability density functions are scalar functions of maybe a billion variables. And so actually calculating that sort of thing explicitly is not only out of the question, but it's not clear what you would do with it once you got it. And so your only hope is Monte Carlo. And from this we have these creatures we call particle methods. Particle method is a type of a Monte Carlo simulation. You do your usual Monte Carlo thing. You start with a sample. Instead of taking your best guess at the atmosphere, you assume, you get your initial condition today by assuming that the atmosphere is some Gaussian random variable. You sample it some finite number of times, and then you run your model that number of times. Say you sample it and get 10 samples, run 10 copies of the model, each with different realizations of what you think the noise is. And that's really the best that you can do. Each of these samples in the jargon is called a particle, because you imagine a particle moving through state space, the trajectory of an individual particle moving through state space. Now, you can't get at the actual conditional probability density, and so if you have observations every time step of your numerical model, and if the observations are linear functions of the state which in general they are not, but in oceans and atmospheres, a lot of the actual data actually are linear functions of the state. You drop instruments in the water and you measure temperature directly, you measure velocity, you actually measure the stuff that's of interest. And in that case, sometimes you can deal with, if not the actual creature that you want, this thing. I'm not sure which way is up with this thing, so I'm.
You just pick.
Here, I could use the old-fashioned way. If you, for each individual particle, if you can sometimes get away with the probability density conditioned upon the observation and the state of that particle itself. So that'll vary from particle to particle, and and that's what they call optimal. That's what has been called optimal for various reasons. And I'm going to show you that this performed well for a shallow water model with about 10,000 state variables, which is a lot. Even though when I submitted the paper, one of the reviewers complained, "Oh, come on, 10 to the 4th is nothing. The weather models have like 10 to the ninth." That's true, but I got only a workstation, and those people have enormous supercomputers. And 10 to the 4th is enough to manifest most of the difficulties with high-dimensional problems. And it performs pretty well, but the problem is these things become degenerate in ways that I'll tell you. And in fact, even under these very, very favorable conditions, we actually do see the degeneracy that was predicted by a number of authors, including Peter Yan, for instance. And at this stage in my work on this, I kind of look back on it, and maybe some of you will disagree, in fact, but it seems like everybody kind of starts off in the same direction in this particular corner of the field. And I should mention before I get going that my unindicted co-conspirators, Alexander Chorin and Matty Mortzfeld at Berkeley, was part of a big project on particle filtering in general. Here's the scheme. We assume that the system we're looking at is governed by a stochastic differential equation. Assume an Ito stochastic differential equation. I want Ito here, even though I'm probably not going to do a proper Ito calculation if you looked at the details. But I want Ito because I want the Fokker-Planck equation. And I assume that the initial condition is nicely Gaussian, a normal distribution about some initial guess that I assume is pretty good with some covariance matrix, some covariance C. And and then at some time t, a vector of observations become available. And then what I want is to find the full conditional PDF of the system at time t. Oh my goodness, have I taken this much time already? I'm on slide 2. And that is the posterior. Now, the probabilists have actually solved this problem. You can write down the Fokker-Planck equation and then calculate this thing directly by Bayes formula. Or if you're actually getting data continuously, you can write down this thing they call the Zaki equation. But direct solution of the Fokker-Planck equation or the Zaki equation entirely out of the question with this many variables. About 20 years ago, some colleagues and I solved the Zaki equation in 44 state dimensions. It took us a month on a ring of about 10 computers. Now, that was 20 years ago. We could probably do a problem like this, maybe in a couple of thousand state variables for the full Fokker-Planck equation. It would probably take a month.
You were solving it in what basis or what method? Spatial approximation.
An enormous Monte Carlo. I think we had 10,000 particles. It's in my paper, 99 Miller Carter Blue. Now, with suitable assumptions, there are linearized methods. There is the Kalman filter. That dates from a paper by Kalman in 1960, where he was mostly interested in things like satellite navigation. And the Kalman filter basically works if you have linear dynamics. you predict it. It's the scheme I mentioned before. If you have linear dynamics, you start with an initial condition. You predict forward until the end of your assimilation interval. And in the weather prediction community, that's 6 hours. You predict forward, and you find out that you were wrong, and then you produce a correction, which is a linear function of the difference between the actual observations and what you predicted them to be. And that linear function is defined in terms of a matrix called the Kalman gain that we actually saw written down in another guise a couple of talks ago that has covariances in it. The other thing is the other thing that's done with the weather centers, the major weather centers actually do, is a thing called 4D VAR. 4D VAR means four-dimensional variational method. The 4 dimensions are, of course, 3 dimensions and time. What they do is they write down a big positive definite functional that is a functional of the the state as they predict it, and that is the deviation from the model and the deviation from the model in the data, and they find a minimum by textbook calculus of variations. And that's what they actually do. But these things are all based on linearized type assumptions. And in the cases where these things fail, your only hope is Monte Carlo.
Can I say something about that?
Yeah?
People in quantum mechanics have gone a long way solving Schrödinger equation in very high dimensions. And by building in specific structure of the solution and looking for approximations in particular subspaces, they've been very successful as measured by comparison with experiment. And it seems that none of that thinking has really been used for Zakai or Kushner-Stratonovich, and could be potentially. I mean, it would have to be different thinking, but and it would not be Monte Carlo based. It would be based on finding a good basis in which to represent solution. And
it's very hard to find such bases in the ocean and atmosphere. I myself have looked for them. You run into any number of lines of thinking in oceanic and atmospheric sciences. Most people will tell you that, oh yeah, the Earth-ocean ice system has some low-dimensional attractor. I'll show you the explicit pictures of a low-dimensional attractor, for instance. It was a tantalizing thought that just ordinary, like singularity theory, will give you a nice basis on which to look at things. But nobody's found such a basis yet, and many people have looked. And as I mentioned, as I commented in Eric's talk, if you start talking about coarse graining and you start to look at these typical kinds of things, say, well, it either sits in this well or this well or this well. If you say that in front of a room full of atmospheric scientists, and I have tried, they will all get up and say, the atmosphere will not do that. And the people who have looked hard for these structures in the atmosphere have generally not found them. And it would be just great if we could find such things. I've looked for them myself. And yeah, I know the quantum mechanicers have managed, and I don't know how.
Quantum mechanics people have done DFT, where you look at the electron density. But if you look at really quantum Monte Carlo, there is no good representation, no calculation that can be scaled to high dimension, right? It's a handful of particles.
But the symbol is that
It's still a handful of particles. But I had a question. I thought that for DVAR didn't rely on linear. It's not a linearized method. It just compute a maximum likelihood.
It computes a maximum likelihood, but it's local. That the only ways it's true that you compute a maximum likelihood, but there's a localization in state space assumption built in because of the nature of the variational calculation. And if you many people have tried to, and it tends to have problems exactly in the case that you illustrated this morning if there are multiple minima. precisely because it's 4D var is exactly textbook calculus of variations. And it, in fact, it does work really well. The atmosphere is terrifically nonlinear. And you can get good solutions from 4D var or variations on the Kalman filter, and they work when they have no business working. It's one of those things that the mathematical rigor sometimes won't justify. But they don't always work. And what do you do when they fail? And I've always been interested in taking these methods and seeing what it took to break them. And they can get useful results, but in many cases they can be broken. And one thing is that the error bars will break before the analysis does. So you'll be getting decent estimates of what's out there, but you won't know how good they are. And very often, if you look at the estimates that come from 4D var, the Kalman filter, you will be misled in either direction. Either the error estimates that you get from the Kalman filter 4D var will tell you you're doing better than you are, or they'll tell you you're doing worse.
So you need the estimate of the state is good, but the variation estimate is bad.
Yeah.
Covariance estimate.
Yeah, and of course you do get covariance estimates, and you also get self-consistency kinds of checks that are available. But they depend on normality assumptions usually, and those things fail long before your analysis fails. Now, the simplest way to do this is you sample the initial probability density function and you choose realizations of the noise process, and then you solve the stochastic differential equation for each sample, and then you resample the result and you keep the ones that you like. And the ones that you like are the ones that came close to that predicted something close to the observations you actually got. But this really doesn't work very well at high dimension. And so our only hope is to choose samples in a way that's informed by the data. That is, we have to find some way to guide the particles toward this posterior distribution. And now we enter the well-worn path that pretty much everybody uses. Here's what actually happens. In the simplest Monte Carlo approximation, the posterior PDF looks like this. You have a bunch of particles with this index super I, and your PDF is a bunch of delta functions with a weight, and the weight is usually proportional to the probability that you got the observation that you got given this particular state. And usually, just to make life easy, because the models are usually such a bear, is to say, well, the observations are Gaussian random variables. And this matrix H is the thing that maps your state vector into the observed quantities. So in the very simplest case of you drop a thermometer in the water and you record the temperature at 6 different depths, this will be a matrix with 6 rows and a zillion columns. And each row will be mostly zeros and have a 1 in the element of the state vector that corresponds to the temperature at that depth, at that latitude, longitude. And so usually you assume that your errors are Gaussian, which can also be a problem. But for now, we're going to get ourselves into enough trouble without worrying about that. So what do people do? And like I said, they do things that are remarkably similar. Well, we'd like to sample this whole conditional probability density, but we can't. And so what do? Well, we come up with another one that everybody calls pi, little pi. It's interesting, wasn't the other day International Pi Day or something like that? And we call that an importance density. And it's a PDF that we can sample that's something like what we want to sample. And then all we do is we multiply and divide by it, which obviously changes nothing, unless you get a 0 divide. These things can't be mutually singular, obviously. But as long as they're not mutually singular, you'll get away with this. And so the expectation of any quantity, if you want to calculate a mean or a standard deviation or something like that, or covariance or what have you, then you'll want to calculate this thing. And so then you simply say, well, okay, I'll keep this quotient because I'll assume that I can calculate it or something like it, and I'll replace this thing by my sum of delta functions. And now I have something I can actually compute. Maybe not computed very well, but at least I have something I can compute. And so importance filters all look something like that. And nearly all and pretty much most of the proposed particle filters, and there are a lot of people working on particle filters out there, and mostly the difference is the way that they choose the importance functions. That's most of. There are people who do completely different things, but mostly it's the way they choose their importance functions. Now, what they call the optimal importance filter is this: that sometimes you can sample this creature, which is pretty nice, and you will find yourself within it, according to, and I guess Mark Bouquet and his co-authors in Monthly Weather Review 2010 put it succinctly, you will only get particles with reasonable likelihood. And it's optimal in the sense that the variance of the weights for any given particle is 0. So no matter what you draw, you get the same weight. But the problem is, as Aids and Van Leeuwen pointed out, that the weights can vary widely among particles. So from one particle to another, you can get very different weights. Still, it's potentially an efficient choice. Now, with more than a handful of observations, what happens is the whole thing collapses on you. And there are a lot of reasons for that, but eventually what the thing that plagues most of these filters is that one of the weights is 1 and the rest of them get to be 0, and you wind up with only one particle contributing to your estimate of everything, and that's really not very good. In particular, your error bars are going to be worthless because, well, you're not going to have any error bars, and so you're not going to be able to solve the problem you set out to solve. And this degeneracy is sometimes called sample impoverishment, and it's the single greatest obstacle to widespread use of particle methods in the oceanic and atmospheric sciences. And this is usually related to what Bellman called colorfully the curse of dimensionality, which people have various dimensional ways of illustrating.
Can I ask you a question out there? So Bickel's work is all about weights collapsing to 1,
Yes.
0 everywhere with respect to dimension. The way you've described it on your slide, the previous one, is more to do with the volume of the data, or equivalently it could be the quality of the data, so that's more variance.
Yeah.
That's a slightly different perspective. Actually, I agree more with your perspective.
Well, if you have a bunch of particles, it's easier to get near one. You map into data space. It's easier to get near one measurement than to get near 75. And if you go back to Bellman's original dimensional argument, then you will decide that the problem is the data space.
Or the quality.
Or the quality of the data. Aids and Van Leeuwen very recently gave a nice heuristic argument that even in the case of the optimal importance filter, that the variance would be the variance in the optimal importance filter would be proportional to the number of independent degrees of freedom in the data, which is, if you're looking at order of tens of observations, is going to be a real problem. Yeah?
So I'm really listening to you from a very wide distance from intellectual space, so I may be completely off here, but when in physical sciences, when we model probability distributions,
I hope this is
by
physical
examples,
This is physics, right?
in my scale of physics, in molecular sciences, when we model probability distributions with samples, and when we have this problem of the volume decreasing, we usually sort of clone particles or resample the space to maintain the number of particles. Is that related to this?
Oh yeah, we do that.
So why do you still have this problem of
Because even after you resample, you still have it, is the short answer.
The thing is that every time we have observations, we have, let's say, I don't know, 100 million observations, all independent. Well,
Yeah.
that's actually true, but
Yeah, even with dozens of observations, you resample. So now the sample collapses, and now I have a bunch of observations, my sample collapses, and so now I reinflate my sample in exactly that way. Next assimilation cycle, if I have a lot of independent observations, my sample collapses again. And I'll show you that graphically in a slide a little ways on down.
Just to say, if you want to represent a density, probability density function in a high dimensional space, including information about the tail, and you want to do that with the sum of delta functions, you just need an enormous amount of them. And so what you say is cloning would work in principle, but you just would need zillions of clones.
But it's because it's sequential, that's the added thing here over and
No,
above.
no, I understand.
It doesn't matter.
Yeah.
No, I mean, how profit?
Yeah. So anyway, the way it sets up, and this is really the way that the way it sets up, and this is the way that the weather centers actually do it, is the way they view it is that you assume that you have that there's some underlying process which some people would call a hidden Markov model, because you can't observe the whole state variable. You only observe what you observe, and you try to infer the state. Again, in concrete terms, the state is, at least from with my oceanographer's accent, the state is velocity components, temperature, and salinity at a three-dimensional grid. The weather models have much larger state variables, state dimensions. And after n steps, we have an observation, a vector of observations I'll call Z, linear related through a matrix X, H to the state vector plus noise. So the observation itself, as in the case that we saw this morning, the observation itself is contaminated by noise whose characteristics we know. We assume the noise is Gaussian with covariance R, and mean given by some unimaginable truth out there that whose features we can only discern by observations. And the idea that pretty much everybody does is you say, well, okay, I know this function f. What I don't know, like I said, the difference between what I think the atmosphere is doing and what the atmosphere is really doing is something random, some stochastic process. So I'm going to add something I call v to every particle, and then after however many steps it takes me to get to the next time at which I'm going to have observations, I'm going to choose v, and I'm going to hope I can find myself in a good place. Now, if I have observations every time, and the observations are nicely linear, so I write this, our second speaker, whose name I forget because I'm jet laggy, wrote down exactly this formula. I can tell you what I think v ought to be. Aids and Van Leeuwen do something like this. They except that we have many steps, and this alpha and capital K are chosen empirically until they get to the step, the very last, the penultimate step, the step just before the last one. Then they do something different. But it would work if they were to use something like that. They just do something empirical, and they've gotten it to work. The implicit particle filter and others, including Eric and Jonathan Ware, choose v by any number of methods, but in the end, one way they could do it is by 4D var. But that's what you do, and then once you've got your v, once you're close to where you think you ought to be, then everybody does something different. Because everybody does something different in order to reproduce the random character of the solution that you're looking at. Now, for particle number I, the probability density function of state vector given observation z and the particle I at that time is given by this thing, everything Gaussian, because I assumed the noise was Gaussian, right? And so this thing and this positive definite functional, something like it, and in fact this is the positive definite functional, very close to the positive definite functional that I referred to, that the weather centers actually use to minimize, to implement the thing called 4D var. But in this case, it's a maximum likelihood. You can look at it as, you can look at this thing as a likelihood function. You calculate the maximum likelihood for a given particle by minimizing this thing, and that gives you, hopefully, that place in state space where you'd like to be, where this particle, the best you can do for this particle given observations. And even though the weather centers spend about 4 times as much time doing 4D VAR as they do doing their forecasts, this particular presentation is one of the easier 4D VAR calculations. The Euler-Lagrange equations for this particular positive definite function will look like this. Lambda is this nice adjoint variable. One run of the adjoint and one run of the linearized model will give you the will give you the increment from the undisturbed function. That's still linearized, and so it is an approximation. But in the weather world, it's pretty good. So to finish the implicit particle filter, you say, well, okay, I can write that importance function as the minimum of this thing, and so I can write the function itself. Let's see, where am I? So if x tilde is the minimizer, I'm sorry, I've gone over this talk a lot, but I'm jet laggier than I thought I was. This likelihood function is now, it's the minimum plus this quadratic thing. Because obviously the gradient disappears, because that by construction. And so this thing is the Hessian of this guy. And now I can sample, and now to get my guess at this particle, I sample a Gaussian distribution with mean x tilde covariance S inverse. Of course, calculating S inverse could be a bear, but I have ideas on how. I've actually done that. I have ideas about how to do it. Next, I'm going to show you how this all works out when you do it. I hope that you followed me this far. This is a shallow water model forced by parameterized wave breaking. This is a near shore model. Near shore is different from coastal. Near shore is inside the surface zone. When people talk about near shore oceanography, they're actually talking about what you see from the beach. And it's really kind of interesting, having spent most of my career in physical oceanography, where lecture 1 in Oceanography 101 starts, the ocean does not work on human scales. The great currents in the ocean, like the Gulf Stream, carry like 100 million cubic meters of water per second, and all the rivers in the world are like 1 million cubic meters of water per second. So that's the fascination of physical oceanography, is that it does not work on human scales. But today we're going to talk about the ocean on human scales. Write down, these are the shallow water equations. State variables are zeta, the height anomaly. That is the height anomaly relative to what would be the undisturbed water, which, as you know, never actually happens in the real ocean. As all of you who've ever stood on a beach know, the momentum, that is, since this is shallow water, we assume that there's no vertical dependence of velocity. So this is the vertical, the momentum parallel to the shore and the momentum across the shore. Geometry, the idealized geometry is a beach with a sandbar. The beach is here. This is where you put your feet. This is the color bars. We're only looking at about less than 4 meters of water. So this is actually what you see on the beach, 250 meters in the alongshore direction, about 200 meters cross shore. Human scales. Very odd. Feels strange for a physical oceanographer to be talking about. Forcing is parameterized from wave breaking. You assume that the waves lose some, they obviously do, lose some energy transfer momentum to the water inshore of the waves when the waves break. And people have looked carefully on that. This is a parameterization by Thornton and Guza, and I thought that this would be a real good place to say, well, look, you read Thornton and Guza's paper, it's got all these approximations. This is a good thing to this is a good place to assume that you're probably wrong. And if you want to look like, if you want want to simulate the real ocean, you add something, you assume that you add the realization of some random process to this, and you assume that that's what nature looks like. Just for I have to assume, I assume my random process is white and time has covariances like this that have mostly Gaussian kind of spatial dependence.
There's some wave breaking, it's dissipative, but also there's some forcing.
The waves are
driven. You're doing wave breaking when you hit the shore.
no, I'm all inside the surf line. If you, I'm assuming that the waves have. So you're standing on the beach, and when I think of what it looks like when I stand on the beach, I see the waves break, and that's what all that white stuff, and then inshore of that you see kind of steady waves that look fairly smooth, and they are forced. And the waves that come in from far away, they come in and they break, and in breaking they transfer momentum to the water inshore. I assume a linear drag, and I'm going to show you two distinct dynamical regimes that for two different values of linear drag, and I hope that you will be convinced, as I am, that we're actually looking at two very different dynamical regimes, and we'll see that the method works fairly well in both. In the high drag case, this is the potential. This is a map of potential vorticity. The little arrows are the velocity. Potential vorticity is exactly that thing that was called Q in the last lecture. In this case, because we're in scales that are too small to take into account the rotation of the Earth, potential vorticity is the quotient of the vorticity and the depth. This makes a certain amount of sense if the background flow is sheared. If you look at the mean flow, and the mean flow is sheared, and the mean flow is going to be mostly the cross-shore direction, the beach is here, the mean flow is mostly that way. If the mean flow is sheared, then each individual piece of water is going to have some non-trivial vorticity to it. As it goes over the sandbar, you look at a piece of water, the length of the column is going to change. And that means that the vorticity has to change, right? Because the term in the Navier-Stokes equations, the relevant term in the Navier-Stokes equation, is vortex stretching. So it's not zeta the vorticity that's conserved with particles, it's zeta over h, the vorticity divided by the depth. And on the big rotating Earth, it's zeta plus f over h, where f is the rotation of the Earth. But we don't have to worry about that here because of the scales involved. It's a little different at low drag. The imposition of noise doesn't do much here at high drag. These pictures look. This is 3 minutes after this. This is 3 minutes after this. This is no noise. This is noisy. The noise didn't make much difference. If there's a lot of drag, it makes more difference when there's less drag. Anyway, but they're qualitatively quite different. If I project down into three well-chosen dimensions, I find out that in the low drag case without noise, I get a nice limit cycle. And if I look at the Poincare map, it all comes here, like you'd expect a nice limit cycle to. Add noise, and it takes a while to draw it, but you still find yourself in the same place, in the same general area in state space. The low drag case, I hope you'll believe, is really intrinsically different. This is the case with no noise. Remember, we had a nice limit cycle. The red curve is the last hour of a 10-hour simulation. Typical time scale is about 10 minutes here. And you can see that this is quite different. I hesitate to call it chaotic because I haven't actually looked at dimensionality of something. It may be some complicated aperiodic motion, and this is a projection down from 30,000 dimensions, remember. I'll try to go through quickly. I know I've used up a lot of time. This is when you put noise on the low drag case, it's all over the map. Come on, is it finished drawing yet? the analysis, these are pictures. The green lines that are different are no noise. This is just to show that the analysis actually does follow. These are 4 measurements. This is a longshore cross-shore velocity. I put in the green lines. Those are the undisturbed case to convince you that the noise really makes a difference, even in the high drag case in detail. But here's the really important thing. These are the particle counts. The blue curve is the actual number of particles after resampling. I use a resampling article. I use a resampling algorithm every time step. The red curve is a measure of the effective number of particles, which is 1 over the sum of the square of the normalized weights. There are a lot of measurements of effective number of particles. I like this one. If one of the weights is 0 and if one of the weights is 1 and the rest are 0, this will be 1. If all the weights are 1 over n, this will be n. And it tracks the actual number of particles that I get after resampling quite nicely. And you can see that here, even in the high drag case, what happens is it stays here and then boom, I lose it all. I get down to 1 particle. So it really does degenerate. This is 15 seconds of a 2-hour run. And any given time, and that's about 100 time steps. Yeah, it's a little over 100 time steps. And it's a little over 100 time steps, and you can see that every now and again the whole thing does in fact collapse down to a single low drag again. And this is now with 50 particles, even though my analysis is actually pretty good. I do get a pretty good representation of the state vector as far as I can tell. Every now and again, and here it's particularly bad, degenerated all the way down to 1 particle, and then reinflate back to 50 particles and back to 1 and back to 50 and back to 1, but mostly it hangs around 10 or 12. And so I haven't, even though in this case, this being the optimal importance filter, in this case I have not escaped the curse of dimensionality, but maybe I've stayed a little ahead of it. Maybe we should think of that great American Satchel Paige who said, never look back, something might be gaining on you. And I guess I'll go through quickly one thing that we might think to do. If we could somehow achieve some dimension reduction, this might be a really good thing to think about, and that is, remember I said that according to a lot of people, Peter Jan most especially, that the problem with the optimal importance filter is that you can get this particle collapse because even though different samples from the same distribution will all have the same weight, there will be a wide variation among particles. Well, maybe if I look back one assimilation cycle, now that I have observations, I look back and I allow my particles back at the beginning to change. Then what? Well, I'm going to assume some distribution I'm going to assume some probability distribution for the particles at the beginning of the assimilation cycle. So remember how this works. I start at the beginning of the assimilation cycle with a collection of particles. I integrate forward for, I don't know, in this case, for 10 or 15 seconds. 10 or 15 seconds, I get a bunch of measurements. And you saw what happens. Even if I get measurements much more frequently than that. Suppose at the end, 10 or 15 seconds later, I go back and I say, okay, I'm going to allow myself to jiggle the initial particles around. Now, in the first place, what am I going to use for an initial distribution? There are a couple of alternatives. One thing I could conceivably do is I could use a kernel method. I don't want to do that. This is looking at 10 particles, 100 particles, 1,000 particles, trying to approximate a two-dimensional normal distribution where the contours of the normal distribution are these gray lines. This is a pretty well thought out kernel method. A kernel method, instead of having delta functions, I have specific functions associated with each point. So this is This is now a linear combination of what they call kernel functions. And even with 1,000 points, it looks pretty jiggly. But if I approximate this Gaussian by the Gaussian I would get by taking the mean of all the particles and the sample covariance and plotting the Gaussian distribution that I get, I do pretty well. So suppose I begin with an initial sample. I take all my particles, calculate the mean, calculate the covariance, get this nice Gaussian function, or maybe I could have several Gaussian functions and sample that. There's a lot of ways to construct a mixture, but today I'm just going to talk about a single Gaussian. Then given the mean, I do 4D var or something. I find the maximum likelihood. I find the Hessian of my nice cost function. I do what I described before. I find a maximum likelihood trajectory. And then I draw a sample from the Gaussian importance function with the mean that I chose. And covariance S, where S is the inverse Hessian of the cost function that I calculated. And that's a nice Gaussian thing, and I resample if I have to, and presumably everybody's happy. This is a picture that is adapted from one of Chris Snyder's slides. If you look at the very simplest, and this is in his setup, where you have a linear dynamics with state dimension n sub x, observe every state variable every time step, and then see how many particles you need in order to do decently. The simplest particle filter, which I'm calling the bootstrap particle filter, is this guy. You need to be above this line, and this is the log of the number of particles. So to get, say, 100 particles, you better get way up there, a couple of thousand. And
So that reflects the Bickle-Snyder theory of being exponentially hard.
yes, this is Snyder's picture. The implicit particle filter that I was talking about earlier, one of these examples where you look for sampling about the maximum likelihood trajectory, you do a little better, but you're still doomed. But the fixed interval smoother, the optimal importance function really is optimal, because you're really drawing from one. You're really drawing from one distribution, and so in fact, this thing might as well be 0. So we may not have beaten the curse of dimensionality universally, but we've beaten it in the Bickle, Snyder, Anderson. There's another guy. We've beaten it in that case. Lee.
But in that case, everything is Gaussian, and you're assuming you're sampling exactly the Gaussian
Yeah.
posterior. So
I know it's rigged, but we beat it. Yeah, it is rigged. Yeah, we're sampling a Gaussian. It's Gaussian. We're sampling a Gaussian posterior, but the deal is that what they say is even in what ought to be that easy case, you're still out of luck with most of what people have tried.
yeah, no, I understand what you're saying.
But
Your posterior is not Gaussian, is it?
no,
Exactly.
no, it's not. No, that's the difference between this and the ensemble Kalman filter, for instance. If you look at a problem that ought to be harder, like the double well that Eric showed us this morning, climate people like to talk about a system with 2 wells. They don't partition things. Talk about a system with 2 wells. It was fashionable in the 1980s to try to look at the climate schematically, where one well was the ice age and the other well was normal conditions, and look at transitions to and from an ice age. You can, of course, have as many wells as you like, which is not news to the molecular dynamics people, I find out, but the climate people don't much do it. And we have particle mostly sits in one well or the other. We have a series of stochastic perturbations, nice Langevin equation. Series of stochastic perturbations eventually will pull it from one well to the next. I promised you the same picture that Eric drew this morning. This is it. This is what happens. This is what the ensemble Kalman filter will do. The ensemble Kalman filter is a thing where it's Monte Carlo, but everything is assumed Gaussian. So your estimate of the state is the mean of your ensemble. Your estimate of the covariance is the sample covariance that you would calculate. And then from that you go ahead and you do the Kalman filter. You see that the real system has undergone this transition, but the ensemble Kalman filter doesn't find out about it till there, because it took that long for it to have enough samples down in this other well before it could see it. The bootstrap filter, that is the very simple one where the samples are not informed by the observation, takes a very long time to see the transition. It happened here. Doesn't understand it until here. And the reason is it takes that long before it put enough particles in the other well, because it has to put particles in the other well. The implicit particle filter tracks it nicely. The fixed interval smoother tracks it nicely. Also, why would I prefer this? Well, in some sense it's cheaper. It's expensive to do that 40 var calculation, but I only have to do it once in the implicit particle smoother, and they both get this nicely. The only wrinkle is that if we look back here, in the actual transition here, the distributions are very, very far from Gaussian, and if you use a Gaussian importance function, you might be making a very poor choice. This is just along one axis. I know this is a one-dimensional problem, but since the assimilation interval is about 200 steps, the actual state that we're estimating is about 200 dimensions, and this is in one direction. The true likelihood function is this blue curve. The likelihood function that we would get from the Hessian, that is from the local curvature, is this green curve. That is to say, it's really flat. Yeah, this is a nice quadratic thing. It curves upward, but way I don't know, someplace off in the street there. And that means that if you assume that you got a Gaussian distribution and this thing is the covariance, you might well just pick something here. When you go to sample your importance function, and oh my goodness, your weight's going to be somewhere around 0, because the true probability of your having gotten that's going to be zilch. And so we have devised a way to refine this basically by an iterative procedure. It's kind of strange. The first time I saw this is the so-called Robbins-Monroe procedure. The first time I saw it, it looked like it couldn't possibly work. You choose a vector. You begin with the inverse, with a covariance given by the inverse Hessian. You choose a vector from a normal distribution whose mean is the maximum likelihood trajectory. Its covariance is the ith iterate of this thing, and you calculate the true and you calculate the importance, and you go back and you calculate the true covariance. You calculate the weight, and then you update by this recipe. Epsilon goes to 0, but not very fast. Think 1 over n. Think epsilon sub I is 1 over I, for instance. So I add a little piece, and with any luck it will converge, and that's how I got this picture. So instead of sampling from this, which is going to be really bad, I'll sample from the red curve, which is not going to be may not look like such a good importance function, but it's a great improvement over the green thing. Wow. So I went over even more than other people did. So the hope is, so the question is, can we devise methods that will give us useful results and avoid the degeneracy that we seek to avoid? Obviously, as we all know, the only hope is to steer particles toward the most probable region of space. And so most of the proposed methods begin with a maximum likelihood calculation, and then they part company, because everybody decides to introduce the random character in a different way. The optimal importance filter can give reasonable results, and there are ways to extend the optimal importance structure beyond this very simple case of having observations every time step and with a linear observation model. There's a paper by Mortzfeld and Joran in JCP that gives detail on how to do that. And one promising method is to use this fixed interval smoother. I'm sorry I went so far over.
Thank you. I think we should have one quick question for Bob, but then we should eat lunch before it disappears. I think we're not going to come out. Does anyone have a question?
I have one. So, this idea of using the optimal weight by computing the minimum of this action is like the obvious thing to do and related to what Jonathan and I
Yes.
supposed to do. But there is a catch with this though, which is that in general, if you do that, the strategy that you have is too greedy, and the estimator that you get can even be worse than the original one. Because as you do the Monte Carlo or the trajectory, in fact, you need to update what is the optimal solution as you calculate it. You seem to not have this problem, and I didn't understand why. Because you make a Gaussian approximation somewhere, or
Because the time, because the assimilation intervals were too short. The way we would run into that problem, and in fact, there are hints of that problem in a lot of. You can see it in Lorentz 63. I read your paper, and you referenced my 94 paper. You look back at my 94 paper. You'll see that, and you're right, and the way and the place where that happens is in places. The situation where that happens is where the assimilation interval is long compared to the physical timescales inside the problem. That's where all of these methods get in trouble. 4D-var gets in big trouble if you do that. And so it's not surprising that 4D-var would get you in trouble here.
Let's just carry on questioning you over lunch. And that's that one. We can start again.